look, we just have a couple more topics left in this class, and then we'll be done. Just to remind you, I told you all this before, but we're covering topics that I covered more in this class, so they're not actually in that workbook. These last two chapters won't be. But I'll give you the notes as we go along, like I did before. As I told you, we're sort of adding topics so that we're in line with what the rest of the state is doing. The sort of topics for this course will change. They've gone from a 2-semester to 3-semester sequence, or LSU has done that, so everybody's following. Anyway, we're adding some additional topics to this class. And so our last topics are going to be on induced voltages and inductance. And some of it's the same as we've seen before, like we'll look at magnetic flux. We've already seen flux when we did gravitation earlier this semester. So hopefully some of that will just be reviewed. And then we'll look at inductors and LR circuits. And that's going to be a lot like RC circuits. They'll be pretty simple, where we're looking at these voltages that change as an exponential function. And then we'll get into Maxwell's equations in the next chapter. I'll post notes online, sort of the notes that we have in class. Of course, I'll also post the screencast and what have you. And then we have an exam coming up. Let's see, May 4th, right? Yeah, so that's not far away. It's just a couple weeks away. And then our finals on May 13th. And of course, the final, just like last semester, be but I'll take it from the 4 exams that we've had. All right. Any questions sort of about what to expect for the rest of the semester? We're wrapping it up. We're almost done. And then you'll be done with physics for the rest of your life. Well, you do a lot of physics in PChem. So when you get into PChem is really just physics all over again. But like you'll do quantum and thermal. So you have a whole class in quantum physics and then a whole class in thermal physics. Which I understand they're kind of fun classes. Let's see, so we're going to look first at induction and inductance. And we found previously that a current causes a B field, a magnetic field. And so we're going to see something similar to this in Faraday's law of induction. So this section that we'll be on deals a lot with Faraday's law. And it just says that a B field, a magnetic field, can induce, or just a fancy way of saying that it can create an E field. At a magnetic field, if I have a magnetic field, it can, under certain conditions, induce an electric field. And more particularly, if I think of an electric field, this electric field will actually cause a current. Alright, so when I'm thinking about a circuit where I have a circuit with a resistor in it like this, and I have a current that flows through that circuit, those charges move because I have an electric field that's causing them to move, to cause these electrons to move. Then we sort of thought of this idea before when we had these capacitor plates, and we have one capacitor plate that's positively charged and one that's negatively charged. And then if I had an electron here, it sits inside of this electric field, then that electron is going to move because of that electric field in that direction. So whenever I have a current, that's because I have an electric field that's causing these charges to move. You got follow me on this? Sort of review so far. So there are two experiments that Faraday did. The first one looked like this, is he just had an ammeter. He had it hooked up sort of like this, where it had a coil of wire. He had a coil of wire hooked up to an ammeter. just like this. And then he took a permanent magnet, where he had a north and a south pole, and he just moved this magnet in and out of the coil. We used to do this in the lab. We don't do it anymore. In fact, in the lab, y'all are doing optics now. I think I've already started optics, right? Yeah, but we don't cover that in this class at all anymore. And unfortunately, that's just the way it's going to be from here on out. This class, we'll do optics. But he took something similar to this, where he had a coiled wire. He hooked it up to an ammeter. Those of you that are in lab, you've used this device. What is this called? Do you remember? Yeah, this is a galvanometer, and it's just a really sensitive ammeter. And so if I hold down one of these show the. Eric, can you see this back here? You can see this thing. All right. So if I hold down one of these buttons, actually, I'm going to ask you to hold down. Just hold down the first button. So if I hold it down, you can sort of see it moving a little bit, right? Now, remember the buttons? They change what on the galvanometer? Remember? Okay. Okay, well anyway, these just change the sensitivity. So if I hold down the first button, that measures the current, an amp or whatever, I don't know what it is. But if I hold down the second button, that'll measure a milliamp or something smaller. So if you hold down that second button, you see bigger changes in the current. So when I pull it out, it causes the current. When I push it in, it causes the current. But notice if I pull it out and just leave it, that it doesn't, nothing happens. So what causes a current here? What must happen in order for a current to be induced? What is it? Okay, so the magnet has to be moving. So what does that say about what causes this current? What has to happen? Not just the magnet moving, but what's happening when you move the magnet? What? Okay, yeah, we're going to get into the flux, but at a more basic level, what happens? Just no, it's not quite that. What I'm doing is I'm just changing the magnetic field. So if I imagine that there is this magnetic field that surrounds this magnet, comes out of the north, goes into the south. I have these magnetic field lines that trace around this magnet. When I put it into this, I'm changing the magnetic field that goes through these coils of wire. And then that induces an electric field around the wire, and then that causes a current in the wire. So I have this electric field set up in the wire, and an electric field in the wire, and that causes electrons to move through the wire. It causes them actually to move different directions. And that's why the galvanometer can actually measure the direction of current. And so, for example, when I pull it out, it goes in that direction. When I push it in, it goes in that direction. See how the direction of the current changes? We'll figure out how to determine the direction of that current by law of Providence as well in just a minute. But Faraday did this experiment, and he found that when he moved the magnet, that caused a current in the circuit. So just like we have here, whenever he moves the magnet, then he would get a certain current going in one direction or the other, depending upon the direction that he moved the magnet. Right? So a few things that he found is that the current occurs when the loop or magnet moves. So you don't just have to move the magnet, you can also move the loop. But the important thing is that they move relative to one another. That you get a greater current when the magnet moves quickly. Whether you're moving the magnet or the coiled wire. When you move more quickly, you get a bigger current. And then the third thing that he found was that the direction of the current was dependent upon the motion of the magnet. Right, and then he did a second experiment that was very similar, where he set up a similar deal. He had his ammeter here. He had a coil of wire set up like that. So he had his ammeter hooked up to a coil of wire. This is just like the previous experiment where he put the magnet into the coil of wire to see what would happen. Except this time, he set up a second coil of wire that ran parallel to that, and he hooked it up to a battery, like that. And so when he turned this circuit on, it would cause a current to flow through this loop of wire. And what would he find over here? I know if I have a loop of wire, what happens? Or a current in a loop of wire, what's it going to do? From the previous chapter, what does it generate? It produces a magnetic field, right? If I have like a solenoid, if we did a solenoid or a ring of wire with a current going through it, it's going to produce a magnetic field. So for example, here, if I have a current flowing in this direction, I'll have my magnetic field coming out of the loop of wire here. And so that magnetic field that's produced by this loop will affect this loop, and just like it did in the first experiment, will produce a current in the blue circuit here. So the current here generates a magnetic field. And that magnetic field here, so the changing magnetic field, causes a current. Just like in the first experiment. Right? Now what's going to happen to the current here? As soon as I turn on this switch, what will happen to the current here? Will it go up or down? Or I'll have a current, right? Well, what's going to happen after I have this switch on? So what's going to happen to the current here? Will it maintain a current or will it go away? It would go away, right? Because just like here, where if I have a magnetic field, right? This magnetic field, or the current, stops when the magnet stops. Even though I still have the magnetic field, I still have the magnetic field inside of the wire, but I don't have a changing magnetic field. You follow me on this? No? Alright, so you found that you get an induced current when you turn on the switch, but the current goes away quickly. Because the magnetic field isn't changing. These are pretty groundbreaking experiments for the time, and in fact, it would lead to the production of electricity that we use today, where we have this magnetic field that's changing that we use to generate a current in a coil of wire. All right, so he came up with this law, Faraday's law of induction. And I just said that an EMF, remember EMF is electromotive force. We use the symbol for this as the script E, but this is also a voltage. It's an energy per charge. An EMF is induced when the number of B field lines that pass through the loop is changing. You can change the number of lines that pass through a loop of wire in a couple different ways. So I have this magnet. At a given point, at a distance from this magnet, the number of B field lines is the same, right? Remember, magnetic field lines, those describe what is the magnetic field at a particular point. So you can imagine these lines that come out around this magnet. They're unchanging for this magnet because the magnetic field of this permanent magnet, it doesn't change, right? It's always the same. And so the way that we change the number of B field lines that's going through this coil of wire is just simply by moving the magnet. Because right now there are no B field lines going through the coil of wire, but then as I move it into the coil and out of the coil, that changes the number of magnetic field lines because it's sampling different space where the magnetic field is located. But what's the other way that you can actually change the number of magnetic field lines that go through the coil of wire? You can move the magnet, right? What's another way? Huh? Okay, you can move the coil too, but to get away from moving things, what's another way? You can change not the motion of the magnetic field, but you can actually change the magnetic field itself. So if you have a changing magnetic field, that will also induce an EMF or a voltage. All right, so the first thing we need to do here is to calculate the magnetic flux. We did this before when we were talking about gravitational fields. Y'all remember the gravitational flux? Maybe, maybe not. But the gravitational flux, or rather the magnetic flux, is a similar idea. We'll use this Greek letter. The magnetic flux is equal to the integral of B dot dA. These are both vector quantities, and we take the dot product of them. This is actually the integral over an area. And if you remember dA before, this vector dA is the vector perpendicular to the area. All right, so if we imagine that we have an area, so if I imagine that this fluid determines my area over which I want to measure the flux, what here is the direction of the vector dA? It's straight up. If we imagine that it's coming perpendicular, or it could be straight down. But we'll say that it's straight up. And then I also want to determine what is my magnetic field, and I'll take the dot product of those two. We'll do some examples here in just a second. So imagine if this is the direction of my magnetic field. Here, the magnetic field and the area are perpendicular, are parallel to one another, with B dot dA. So what is going to be the dot product of B and dA? Is it going to be, let's say that they both have a value of 1. What is my dot product of B and dA? It's 1, right? Because remember my dot product is going to be dA cosine theta, and here my angle theta between the magnetic field and the area vector are going to be 0 degrees. So if I have a magnetic field vector that's in this direction, and it's going through an area that's like this, then that means that the flux is going to be at its max value. However, if the magnetic field vector is at an angle like this, that means that it's going to be some lesser value, because I have to multiply times that cosine theta term. And then finally, if my magnetic field vector is in this direction, what is the flux through this fluid, through this area? It's 0, because I'm taking the dot product here. And if, in this case, my angle between the area vector is in this direction, and this vector, which is my magnetic field, that's 90 degrees. And of course, the cosine of 90 is equal to 0. And you can sort of think about it too, that I have this magnetic field in this direction. That means that there's nothing going in this direction. So there's no magnetic flux through this area given by the fluid. All right? I went hula hoop for you, but I was hula hooping yesterday with some kids. And my wife said that I looked kind of goofy. But she said it looked like I was having a good time. And I was able to keep it up for a while. Do you want to see the Yeah. I think I'm pretty good, actually. Go to the back. Okay, I know this isn't related to following the car. She said I sort of think that I'm all hunched over. That wasn't very good, but you get the idea. Y'all can try it later if you want. You can demonstrate for the whole class. I said we saw flux before when we were doing gravitational flux, but it's just the dot product of those two vectors, and then you take the integral over them. Right, so let's sort of write that out. These surface integrals, you may or may not have gotten to them in your calculus class. Yeah. You do the dot product first. But in practice for us, we're just going to do a summation. So we're not going to actually do any integrals with this. We'll see some dot products of the integrals, because y'all probably haven't got to that yet. That's correct? Surface integrals in your calc class? Where you integrate over a surface? Yeah, probably not. But we've done some in this class as we've gone through. All right, so if the B field is perpendicular, the B field is perpendicular to the loop, right, where we have something that looks like this. Here's my loop of wire, my magnetic field looks like that. In this case, the area vector, which is perpendicular to the actual loop, and the magnetic field vector are parallel, or anti-parallel as it may be. But regardless, theta is equal to 0 degrees, so B dot dA, which is B dA cosine theta, are 0 degrees. This will just be equal to B times dA. And we'll deal with cases where our magnetic field doesn't change with area. So this integral is pretty easy because we'll just take the B out of the area, or out of the integral, and so we'll just be looking at the integral of dA, which will just be the area of our surface. All right, so this is equal to our flux, and the unit that we'll use for flux, magnetic flux, is the Tesla, which is the unit for the magnetic field, times square meters. So it's Tesla to square meters for our units. All right, can I go down from here? Give me about a second. Hey guys, I have your exams too, by the way. I'll hand them back at the end of the class. It seems like it's been a while since we've taken the exams, right? All right, so let's look at Faraday's law again. So the EMF is equal to the rate at which this flux changes Alright, so that goes back to this idea that if I change the magnetic field a lot, that if I make this go in at a fast rate, it changes the current a lot. I make it go in very quickly, but if I make it go in very slowly, then the current doesn't change very much at all. So the more that I change the magnetic flux, that means the greater my my EMF is going to be, the change in potential. Also, we'll see, and he just found this experimentally, but the EMF generally opposes the change of the B flux, the magnetic flux. I'll show you what that means in just a second. But basically, the coil of wire is setting up a magnetic field. Like there's a current in the coil of wire, and that generates a magnetic field. Generally, that magnetic field opposes the direction of the magnetic field due to the permanent magnet. I'll show you some pictures here in just a second, or we'll sketch out some things. All right. But the principle behind this is that the EMF is equal to the negative of the derivative of the flux with respect to time. So the rate at which I change the magnetic flux from the magnet will give me the potential, or the EMF, that is produced inside the coil of wire. We'll do some examples soon where we actually calculate what is this voltage or what is this EMF that we produce. Also, this is just for one coil of wire. This is for one turn of wire. But for multiple turns, if I have n turns of wire, it's going to be very similar, but the EMF is just the negative of n dphi dt. So the more turns of wire that I have, the greater the potential is going to be, or the EMF. Alright, so just sort of stand back. Our magnetic field, when I have a changing magnetic field, what does that create? If I have a changing magnetic field, it induces a what? An electric field, right. And then the electric field actually causes this change in potential. Because remember when we were talking about electric fields earlier, if I have this two plates set up, I have an electric field in between them. If I have positive and negative charges on those plates, there's a change in potential between those two plates. Right? I have high potential and I have low potential on this side. And because there's a difference in potential, that's our EMF, that's that strip E. And I'll also have a current flow between them. So for example, if I have a positive charge here, it will move in that direction. So our changing magnetic field sets up an electric field, and because of that electric field, I get a change in potential, and then because of that change in potential, I have a flow of charge, or current. I sort of said this already, but let me write it out. There are three ways to change the magnetic flux. With time, I can change the magnitude of the magnetic field. Within the coil. I can also change the area of the coil. Remember, because our magnetic flux is given by this idea that phi is equal to the integral of B dot dA. So the first thing that I can do is I can change B. The next thing I can do is I can change A, and that'll change the magnetic flux. I can change the area of the coil. The third thing I can do is what? So I can change the magnetic field. I can change the area. What's something else that I can do in order to change this magnetic flux? I can change the magnetic field, the magnitude of B. I can change the area of the coil. What's the other thing that I can do? It has to do with this dot product here. What's the angle? Change the angle, right? You can change the angle at which they interact. So that will also change the magnetic flux, right? So we have this maximum flux. If this is my B field and this is my area, this is maximum flux, less and less and less flux until I get to zero flux. So that would cause a change in the current here as I move this across an angle. We saw that before when I showed you a video where it's like a little simulation of the windmill. Remember the windmill? They actually changed the angle, right, because it rotated, and that changed the angle of the magnetic field vector with that vector dA. So the third thing that you can do here, you can change B, you can change A, or you can change the angle between B and A. Alright, and that comes about because of our B dot dA is equal to BA cosine theta. And if I change that angle theta, then it will also change the magnetic field, or the magnetic flux, rather. Alright, let's do a quick little check here. Let's say that I have B here. This is a plot of B versus T. Right, I'm going to call these different regions. This will be A, B, or excuse me. I have three regions here, and I want to know where is the EMF the largest. Is it A, B, C, or D? Hold on, let me get my clicker up. Alright, where is the EMF? I have the changing magnetic field as a function of time. Where is the EMF the largest? I'm going to give you some options. Is it A, B, C, or D? Or is it A and C? So this will be A, B, C, D. And then this is the option E, which is either both A and C have the same EMF, which is the largest. All right, so where is the EMF the largest here? I'm going to stop at 105. 105. So these are your answers. Let's see. B is right. Remember, because our EMF is equal to the negative of d phi dt, or d phi dt. We can change our dp in a couple of different ways, or three different ways. We can change B, we can change A, or we can change the angle between them. And here, what am I changing? B, A, or the angle theta. I'm changing B, right? So this just shows B with time. And we want to find the place where B changes at the greatest rate. All right, so where the integral, or excuse me, the derivative of B with respect to T is the greatest. And where does it change with the greatest rate? All right, where B, where it's the steepest. So here it changes a large amount over a short amount of time. All right, where is the EMF the smallest? Just looking at the magnitude of the EMF here, we're not considering the size, just the magnitude. All right, I'm going to stop at 25. 25. Okay, good. E's the right answer, but C, I understand. You put C. C is one of the right answers, but also A has an EMF that's the smallest. What is the EMF at points A and C? It's zero, because the magnetic field is not changing. At least we think it could be zero. It could also be that they're changing the area or the angle, but we'll assume that that's not the case. right, let's do an example. Unfortunately, there are no old exam questions on this for y'all to practice, but I'll have some homework questions for you later in the week to practice on. I'll make some videos like I did as well. And for the exams, I'll follow pretty closely to the homework problems. So if you can understand those and able to work through them, they'll be similar. They'll be different a little bit, but they'll be largely similar. All right, so let's say I have a solenoid. And remember, a solenoid looks like this. It's a coil of wire. Right, that's a solenoid. We'll see that later. It's actually, we'll call it an inductor. But a solenoid has a current. That current's 1.5 amps, and it has 220 turns per centimeter. That means that in 1 centimeter of your solenoid, that there are 220 turns of wire. All right. The diameter is 3.2 centimeters. We put a coil. Call it C, inside of it. With diameter equal to 2.1 centimeters. So what I'm doing here is I'm just putting another coil inside of that first coil. When I do that, the current in the solenoid is decreased to 0 amps over 25 milliseconds. What is the EMF in the coil C? Right, so I have this first solenoid. It has a current in it. It has 220 turns per centimeter and a diameter equal to 3.2 centimeters. And I put a second coil inside of the solenoid. It has a diameter of 2.1 centimeters. And then the current in the solenoid decreases to 0 amps over 25 milliseconds. What is the EMF in that first solenoid, in that first coil that I put in? Now first I want to tell you, you don't have to know this right off, but the magnetic field due to a solenoid is equal to mu naught I times N, where N here, this is the number of turns per length. So N is this value here, or 220 turns per centimeter. All right, so I know that my EMF is equal to negative N d phi dt. All right. And what then is my final magnetic flux? What's my final magnetic flux going to be? Alright, our final magnetic flux is going to equal to 0. The unit for flux are Webers, or WB. And it's just equal to 0 because in the final case, my current is equal to 0. And my initial magnetic flux is equal to B times A. That's assuming that my magnetic field is perpendicular to my area, but for a solenoid that is the case. So this just goes back to my flux is the integral of B dot dA, but it simplifies to this because they're in the same direction, and I just integrate over that area and it just gives me the area. All right, so my initial magnetic flux is BA. The magnetic field of my solenoid is mu naught I times N. That just comes about from here, times the area. And then I can calculate then what is my magnetic flux. That mu naught I is 4 pi times 10 to the minus 7. You have that on your equation sheet, but we've used it before. Times 1.5 amps times N, which was 220, but in SI units that's 22,000 turns per meter. Times the area. The area here is pi r squared, and that's equal to, for my solenoid, 3.464 times 10 to the minus 4 square meters. Alright, you with me on this so far? Sorta, kinda. If it doesn't make sense to you right now, don't worry, we're going to come back to it. We'll work through some more examples. But this is my magnetic flux then. If I calculate it, I find that my initial magnetic flux has to have a value equal to 1.44 times 10 to the minus 5 Webers. All right, and now I want to know what is the induced EMF. All right, remember my induced EMF is equal to N d phi dt. How do I find this change in my flux? How do I find my change in my flux? What is that in basic ideas? It's a change in something, right? Over time. Everything okay? It is supposed to be negative, but here we're just looking for the, I'll put a negative there, but we're really just looking for the magnitude. All right, how do I find my change in flux, d phi dt here? Right, it's just final minus initial over my time. So this is going to be negative N, or I'll just find this d phi dt first. This is just phi final minus phi initial over t. That's 0 minus 1.44 divided by 25 milliseconds. And so that gives me my my change in the flux, which is going to be 5.76 times 10 to the minus 4. Let's see, that's in Webers per second. All right, but then if I want to find my EMF, this is going to be just looking for the magnitude of that EMF is just N times that 5.76 times 10 to the minus 4, where N is 130. And so that's going to be equal to 7.5 times 10 to the minus 2 volts. All right, so what we did here is we just found what is the changing flux, right? Calculating the flux at one point, and then calculating the flux at the final and initial points. And then our EMF is just a change in that times the number of turns of wire that we have. We'll come back next time and we'll do some others. I also want to get into Lenz's law a little bit today as well. Y'all feel okay with this? Oh, that's just what it was. Let's see. Oh, I didn't write that down. I'm sorry. I'm not sure. I don't have it in my notes. I'll have to go back and look. Let's see. Yeah, I must have had a length of the coil. I'm sorry, this is just the number of turns in that coil. Excuse me. So here, N, this is the number of turns in the loop, in the coil. C, that coil that we put inside of the other coil. We'll come back next time and work another problem. Would that be useful for y'all? A similar one? Okay, we'll come back next time and do that. Let's look at Lenz's law, though, for just a few minutes. We use Lenz's law. This came shortly after Faraday's law. It determines the direction of an induced current in a loop. It basically says that an induced current has a direction such that the B field due to that current opposes the change in the B flux. That induces the current. Okay, so I'm going to induce the current inside of my coil. So if this is my coil, for example, I induce this current, and the magnetic field that it generates is going to oppose the change of the magnetic flux that actually caused the current. That might not make sense right now, but let me draw a picture. So let's say, for example, I have a coil of wire. This is sort of in the page here. And then I bring in a magnet like this. This is my north, this is my south, and so my magnetic field here is in this direction. My magnetic field is in this direction as it goes into this loop. So the magnetic field that's generated by the loop then, this is the B field of the magnet. This is going to be the B field of the loop. Those two are going to be opposed to one another, and so the current then in this loop, let's see, is going to be in this direction. Remember we did this last time with the right-hand rule, where I imagine that this is the loop, instead of sort of coming out of the page like this. I have this magnet that's coming into it, so the magnetic field of this loop is going to be in that direction. That means that, that my current then has to be coming up here and down here. This loop has to produce a magnetic field that's opposite the magnetic field of the magnet that's coming into it. And so that means that my current is in this direction, so that my magnetic field goes out in this way. Right? That changes depending upon the direction of the magnet. So for example, if I switch the magnet around, where this is my loop now, this is my magnet south and north. Now my magnetic field is in this direction, So this magnetic field will be in this direction. All right. We'll stop there. It also depends upon the direction that the magnet is changing. So, like for example here, you notice when I put the magnet in, the current is in one direction, but when I pull the magnet out, the current goes in another direction. But I haven't changed the orientation of the magnet, I've just changed the direction that it's traveling, one way or the other. And so that'll be important too, not just the shape of the magnet or the orientation of the magnet, but also the direction that it's traveling. Okay? Yeah, yeah, that's okay? Sort of, kind of? We'll do some more practice next time. It's always fun to practice. All right, let me hand back your exams. Your grades are online. I've already posted the things. This thing's already emailed. So the number on the top of this is the number of figures are. I did pretty well. Have a good day, okay? We'll have some more quicker questions next time for this section. I'll put up some homework as soon as I can get it up. This week sometime.